the science guy.
Let's talk about acids and bases. Fill. What's pH? Oh yeah, that guitar solo. Science, woo! Fill.
Fill by the science guy.
Hey guys, on today's episode of Phil 9, we're going to be talking about acids and bases. Some topics we're going to cover include pH, indicators, buffers, dilutions, and titrations. Hope you have fun!
Before we start our experiment, let's freshen up on our lab terminology. This is called a Erlenmeyer flask.
This is a graduated cylinder.
This is a watch glass. And don't forget, wear your goggles.
There are three definitions of acids and bases: Arrhenius, Bronsted-Lowry, and Lewis. The Arrhenius definition defines an acid as dissociating in water to form hydrogen, H+ ions, and a base as a substance that dissociates in water to form hydroxide, OH- ions. The Bronsted-Lowry definition states that an acid is a proton donor in a solution and a base is a proton acceptor. The last definition was created by G.N. Lewis. He defined an acid as an acceptor of electron pairs and a base as a donor of electron pairs. Let's practice. Identify which is the acid and which is the base in the following reactions. Now, let's identify the conjugate acids and conjugate bases. To do this, we can focus on the right side of the equation. The compound or ion, which would act as an acid in the reverse reaction, is called the conjugate acid. The compound or ion, which would act as a base in the reverse reaction, is called the conjugate base.
The volcano experiment represents a neutralization reaction. In this reaction, the vinegar, or acetic acid, acts as the weak acid, and the baking soda, or sodium bicarbonate, acts as the weak base. Once the reaction goes to completion, CO2 is formed in the form of bubbles, and sodium acetate, which is the byproduct, which is a salt of the weak acid. And then if we were to proceed with this experiment, this sodium acetate could act as a buffer in subsequent experiments.
So what exactly is a neutralization reaction? Well, it's when an acid and a base react to form water and a salt. In the reaction, the combination of H+ ions and OH- ions generate water, and the metallic ion from the base replaces the H+ ion that the acid lost to produce the salt. The neutralization of a strong acid and a strong base has a pH equal to 7, whereas the neutralization of a strong acid and a weak base will have a pH of less than 7. Conversely, the resulting pH when a strong base neutralizes a weak acid will be greater than 7. Remember, strong beats weak. The strong acid or base in the reaction will determine if the final product has a pH greater or less than 7.
So we have half a mole, which is 42 grams of baking soda, and we have 60 milliliters, which is 1 mole of vinegar, and we want them to be in this half mole to 1 mole ratio so that the vinegar is in excess and the reaction goes to completion.
Okay, so we transferred our 42 grams of baking soda into this Erlenmeyer flask, and we've transferred 60 milliliters of acetic acid / vinegar into this cylinder. As shown in the clip, we know this reaction is occurring because of the carbon dioxide bubbles produced. This only forms as a result of the progression of the reaction. Another change that occurs as a result of the reaction is a change in pH. 4 drops of universal indicator were added to the vinegar so that we could observe the change in pH. The solution changed color from red to yellow, showing a pH change from about 0 to 2. The indicator added only changed color because the pH changed, which can only happen if the reaction is happening. Since CO2 is in the gaseous state and the two reactants, baking soda and vinegar, were in the solid and aqueous states respectively, the entropy of the system is increasing. As we observed in the experiment, the reaction proceeded without any other additives to the system. Thus, the reaction is spontaneous and driven by entropy.
So where can we see this in our daily lives? Hydrochloric acid is found in gastric juices secreted by the lining of the stomach. HCl is needed by the enzyme pepsin to catalyze the digestion of proteins in the food we eat. Heartburn is a symptom that results when the stomach produces too much acid, which is also known as hyperactivity. Antacids are bases used to neutralize the acid that causes heartburn. Despite the many commercial brands, almost all antacids act on excess stomach acid by neutralizing it with weak bases. The most common of these bases are hydroxides, carbonates, and bicarbonates. Another location in our body where acid is present is in our mouth. The bacteria in our mouth that is not washed away by saliva reacts with the sugar in certain foods and forms acid on the teeth. An excess amount of acid is detrimental to the teeth as it weakens the enamel. Enamel is the hard protective covering on teeth made of mineral crystal. When the mineral crystal is exposed to too much acid, it begins to break down, which can result in a cavity. To try and combat this, many types of toothpaste contain mild bases in their ingredients, such as sodium fluoride or sodium bicarbonate. These bases are what neutralize the acids. Foods and drinks that cause a large buildup of acid in the mouth include soft drinks, fruit, and honey. To prevent acid buildup, it is important to brush your teeth after eating these types of foods to not only neutralize the acid, but also to remove the bacteria.
Now let's talk about acid rain. Here's the world. Instances of acid rain have dramatically increased over the past decades. Why does this happen? Acid rain is created through a cycle. It starts with burning off fossil fuels by industrial plants. This releases SO2 into the world. Gaseous SO2 reacts with atmospheric water vapor. This forms sulfuric acid. In addition to some SO2 dissolves in raindrops, forming the strong acid H2SO4. Coal-burning power plants produce particularly high levels of nitrogen oxides, which end up in acid rain.
You may be wondering what pH is. Well, pH is a measure of the hydrogen ion concentration in a solution, which tells us how acidic or basic the solution is. There are tons of ways to measure pH of a solution. For example,
measuring pH using an indicator, hydrogen electrode method, quick hydrogen electrode method, intermediate electrode method, glass electrode method, semiconductor sensor methods, pH, and imaging pH slips.
pH is calculated on a scale of 1 to 14, but it is not limited to this scale, meaning pH can be negative. 1 means that the solution is acidic, with many hydrogen ions. 14 is basic, with many hydroxide ions. pH is calculated using the negative log of the concentration of hydrogen ions. pH works in a tenfold fashion, meaning that when you multiply the volume by 10, the pH increases by 1. Another concept related to pH is pOH. pOH is the opposite of pH, which means it's the concentration of OH minus ions in solution. And it is calculated using the negative log of concentration of hydroxide ions in solution. When measuring pOH, 1 is very basic and 14 is very acidic. Dr. Ari Chen, PhD in chemistry. We brought him down today just to speak to you guys about pH indicators.
Thank you so much for the introduction, Dr. Phil. I'm actually quite well versed in the field of pH indicators. What questions have you prepared for me?
We have tons. First I want to start off with, what is a pH indicator?
Well, a pH indicator is a compound which tells us a color change over a range of pH values.
Wow, that's very smart. So, our second question is, what happens on the atomic level?
The compound goes into a solution where there are ions, and the ions cause the compound to dissociate, which leads to a color change.
Wow, thank you, AJ. Oh man, this guy's a man.
What is a titration? A titration is a technique in which a burette is used to titrate specific amounts of titrant into an analyte to determine its concentration. We use them for acids and bases because they are very precise, and with the addition of an indicator, the point at which the pH changes is useful in determining the concentration of that substance or analyte.
Depending on the titration, the equivalence point may not always be neutral. For the first graph, it has a pH of 7 because both strong acids and strong bases completely dissociate. Since the definition of the equivalence point is that the moles of titrant has to equal the moles of analyte, the equal amounts of H plus and OH minus will cancel each other out. However, in the second example, the strong base is being titrated into a weak acid. Since the weak acid will have a smaller dissociation constant, less H plus ions will be present, and the NaOH will have neutralized all of the H plus before the equivalence point, leading to a basic pH. The opposite is true for a strong acid with a weak base, in which the equivalence point will have a pH below 7. This is why using the correct indicator is important. Since the concentration of the analyte is unknown, the color change of the indicator tells you the equivalence point and allows you to calculate the concentration.
Got it? Got it! Hey guys! Sure.
Now that you know a little bit more about what pH is and what it means for a solution to be basic or acidic, we are now going to explain to you how 4 common household items, Windex, antacid, honey, and vitamin C, identify as either being basic or acidic by nature.
So here we have Windex, which is a cleaning product, and as you can see by the label, it contains ammonia, and we have it here in a beaker, and we're adding the universal indicator. As we stir the solution, we see a color change, and this means that the solution right now is basic.
This is antacid. It is used to treat heartburn and stomach pH imbalance. It's very basic. This is honey. It's made by bees. You can buy it at the store. It's acidic.
Vitamin C, and it's also been dissolved in water and ground up in a solution. And here's the label. So we're adding the acid-base indicator, and we're already seeing some color. And there you go, that's the color change. And because of its color, we know that it's acidic.
So what happens when we put dry ice in water? Well, we know that dry ice, CO2 solid, sublimes to form CO2 gas. And this is an endothermic process. So what does that do on the system? Well, that means it takes energy from the water, which we submerged it in, and therefore, since this is our dissociation equation for water, if we take energy away from this equation, that means, from this reaction, that means that it'll actually shift to the left, which means there will be less dissociation of H3O+. And what does this mean? Well, that means that the value of Kw, which is our dissociation constant, will actually decrease. And since we know that Kw is equal to Ka, the acid dissociation constant, times Kb, the base dissociation constant, actually we expect the pH to increase, or in other words, become less acidic. But when we put dry ice in water, we see from the experiment that actually the pH decreases dramatically. So what's really going on here? So what's really going on behind the scenes on a chemical level is that when the CO2 solid sublimes to form CO2 gas, this gas actually reacts with water to form H2CO3, or carbonic acid, which is a weak acid. And carbonic acid goes through not only one dissociation to form H3O+, but a second dissociation to form H3O+. And this is what is lowering our pH in our experiment? So in this experiment, we had vinegar, which is acidic and it's 2.7 pH, and we added baking soda, which is a base, and we mistakenly did not realize how much product we would get. However, we can derive from this experiment is that when we add a base to an acid, like this, we can get a good, solid pH change, which changed to 4.6 in this scenario.
Little Phil is very curious to know why he is still alive, despite having exercised so much, which causes many chemical changes in the body, which causes the pH of the blood to drop. See, if pH drops below 6.8 or rises above 7.8, death may occur. Fortunately, we have buffers in our blood to protect us from large changes in pH.
Buffer? What's a buffer?
A buffer is a solution of a weak acid and its conjugate weak base that resists changes in pH upon the addition of an acidic or basic substance.
Here we have 2 beakers of normal H2O and 2 beakers of buffer solution made with sodium acetate and vinegar, aka acetic acid. So we're going to look at the pH of the water first. This should be relatively neutral. Neutral is close to 7. Okay, so it's a little bit low, but that's okay. We can deal with that. And now we're going to test the pH of the buffer solution. The pH of the buffer solution is around 5.3. Okay, now let's see what happens when we add a strong acid, HCl, a 1 molar solution, which we have in this graduated cylinder here, to the water. Really? Yeah. Because the water has no buffer, we should expect the pH to go down dramatically. Going down means it's more acidic. Okay, now let's see what happens when we add the same amount of 1 molar HCl, which is a strong acid, into the buffer solution. Remember that the buffer solution had an original pH of around 5.3. Notice how it hasn't dropped as dramatically as it has in the water. This means that we have made a successful buffer solution which doesn't change pH as easily.
But what does any of this have to do with our blood?
Well, little Phil, there are 3 types of buffers in our blood. Let's learn more about them.
Okay.
The most important is the carbonic acid bicarbonate buffer. During exercise, muscles use up oxygen as they convert chemical energy and glucose to mechanical energy. This chemical change lowers the pH in your blood. Carbonic acid, or H2CO3, is a weak acid and is therefore in equilibrium with bicarbonate, or HCO3- in solution. When significant amounts of both carbonic acid and bicarbonate are present, a buffer is formed. Under normal circumstances, there is much more bicarbonate present than carbonic acid. The ratio is usually 20:1. As normal metabolism produces more acids than bases, this is consistent with the body's needs. The blood, with its high base concentration, is able to neutralize the metabolic acids produced. Since relatively small amounts of metabolic bases are produced, the carbonic acid concentration in the blood can be lower. Since carbonic acid is not stable in aqueous solutions, some of it decomposes to form carbon dioxide and water. The respiratory system is responsible for removing the carbon dioxide.
Thank you guys for watching, and remember, don't make any chemistry jokes because there might not be a reaction. That's a wrap. I hope you enjoyed the video, but that's